We continue the VOPS series with part 4, Geometry Interactions. In Houdini there are several ways to use geometry for simulations. In this part we cover what different operations do and when to use them. In Houdini there are many ways that different geometries can talk to each other. So we can have any geometry and we can grab attributes from other geometries and combine different attributes like position or velocity or really any attribute. So this will come up all the time in VFX. So let's say for example we have a particle simulation that starts off the ground and we want the particles to slowly form the shape of a human or any other shape. We would have to know how to access information from that human mesh or geometry and how to apply it in our simulation. So I will show you some of the main ways that we can achieve this interaction between geometries and the differences between them. So I will start with a geo container and I will just drop a grid and maybe just scatter some points, and I will increase the total count and we will plug this inside an attribute VOPS. So let's step inside. And probably the simplest way to grab attributes from a different geometry is going to be with an import point attribute. So let's drop this node, and we are already familiar with this node. We've seen this used a bunch of times, but let's just do a quick recap. So this will ask us for a file, which is going to be the input from outside of our attribute VOP. So if I step outside, it's going to be one of these other inputs here. And while we are here, we can do an add, and let's just create a simple point at origin, and I will place this as the second input. So now I can go inside and we can point the OP input to our file. We could also just use the input mode here and set this to second input, and we will no longer need the connection, but let's just leave this as a file with the wire. And then it's going to ask for what attribute we want to import. So we can type this here, whether it's position, so P or N or V. So let's just keep this as position, and then the PT number. So if I go outside, because we are only working with one point, this is always going to have a point number of 0. So I can turn on the point display and we can see that this is 0 over here. So let's go back to our geometry, and I can just promote this to a constant, which by default is 0. So this will now point to the correct point in our geometry, so the only point really. So in the vector lessons, we use this point position to create a vector that points from the geo to this point by subtracting the vectors. And I want to introduce you to a new node, which is one of my favorites, and that is the distance node. So let's drop down a distance. Now this is very straightforward. It will output a float value, which is basically the distance between two positions. So in our case, we are going to use the position of each point. And for the second one, we are going to reference our position from the second geometry, so our single point that is in the center of the scene. So now if I plug this result in our color so we can visualize this value, we have this small gradient here from black to white, right in the center. And what we can do here is I can drop down a fit range and I can increase the source max, and this will help to spread out this gradient. So as I start to increase this, we can see that the gradient spreads out, and I will reverse the destination mean and max. So let's set this to 1 and this to 0, and now if I decrease the source max, hopefully we can see more clearly the result that we will have here. So now basically I can just go up, grab my point, and this distance will follow the center of our point. Or actually just the point, because it's only one point, so it's always going to be the center. So I can move this around and we can compute this gradient from any place, and I can go back inside and adjust our fit max to spread out the gradient. So this is already pretty handy. A lot of times when I had to make a simulation, I wanted the density to be higher in the center. So let me just go ahead and reset the position. So I wanted the density to be to have a higher value in the center and fade out towards the edges, so this is really helpful. And we can also use a ramp parameter after our fit, and if I set this to a spline ramp and go up, I can add a point here in the middle, and we can even create this sort of like border. So I can adjust these values a little bit and we can have something like this. So if I'm doing a fire simulation, we can turn these points into the source, and the fire would be right on this border, and we can still go back inside and combine this with a turbulent noise. So if I go to the position from where we get the distance, so from the position of each point, I can mess up that position by using a turbulent noise, and I will set this to a 3D noise, and let's use noise type simplex. So if I add this to our position, and I'll plug the P inside the pose, and we can now add the values on our position. And now if I play around with the noise settings, we can see we get a much more interesting source. And I can play around with the frequency and stuff like that, and I can also animate the offset, so I would be able to add some animation to this as well, like so. And this setup here I did a million times in production to create interesting sources for simulation. So this import point attribute is working fine when we are dealing with just one point, so we can actually manually point it to the point number, to the correct point number, by doing a constant here and setting it to 0. But what happens if we have multiple points that we want to interact with our geometry? So if I go up, let's go ahead and delete this node, and let's do another scatter from the same grid. And if I go to this result, let's maybe just scatter a few points. Okay, so let's say that we want to use these points to generate the distance values. So I will plug this in the second input, and if I check the result, it will only consider now the point number that has a value of 0. So if I turn on the point number display, we can see that this one here is going to have a PTNum value of 0. So this is the one where we generate our distance from. So if I preview the result, we can see that it's this one over here. But let's say that we want to consider all of the points, so let's maybe template our second input, so our second scatter. We can now use a Nearpoint function to determine, based on our position, which of these points, so from our second scatter, which of these points is closest to our own position. So if I go back inside and I drop a Nearpoint node, we will point the position to our own position. So I will place this here, and the input will be the second input. So we want to look in our second scatters, so all of these white points over here. So now this will give me the point that is closest to each of our other points. So maybe this is a little hard to see with the black background. Let's press D and set the background to light. Alright, so now each of these black points will look in our second input. So again, it will be this scatter over here, and maybe I can even turn on the point size for all of these points and make them bigger. So from our scatter, we are going to look for each point in our second input, and based on our position, we will be able to identify which of these points is closest to us. So if I go back inside, this will return the point number, so I can plug this in our PTNum. So now this will be the result, and let's maybe go back to a dark background. So if I grab this feed value now and adjust the source max, and let's maybe go up and also reset our ramp just so we get the normal 0 to 1 value, we can now adjust our source max, and we can see what this is doing for us. It's going to grab the nearest point from our second input, and it's going to generate the distance from that point. So this is how we can have multiple points as our second input, and I can increase the total count here, and we can see we get this really nice and interesting pattern. So I can play with our fit ranges further, and I can also do the same thing that we did with the ramp. So I can also create this and create sort of like the same thing we did that gives us a border, and maybe I will just scatter more points. And we can also go to our noise and we can play with the amplitude. So this is one way that we can use the Nearpoint function. So we usually have to combine the Nearpoint with this import point attribute in order to retrieve the attribute that we are actually looking for from the second geometry, because this only outputs the point number. So by itself, like this, it's pretty much useless to us. So this import point attribute is very useful, and we can see that we can combine it with different nodes in order to retrieve the point number that we are interested in. We can of course use it on the same geometry that is modified in some sort of way. So I'll go ahead and let's get rid of all of these. Let's actually go up to our scatter, and I'll get rid of our second scatter here. Maybe I'll just delete this attribute VOP. So let's say that this geometry, for whatever reason, we need it to go through a different process in order to create an attribute or to modify the position. So let's say that on the right, I will just simply do an attribute noise vector, and I just want to mess up the position a little bit. So let's go to this. I'll set the vector here to P, and I just want to displace the points, and maybe I'll just increase the element size. So this is just to give you an example, but let's say that we achieve this result through some simulations or through some other different methods, and then on our original geometry, so on this regular scatter, let's do another attribute VOP. And let's say that this chain on the right, so what we are inputting here on the left, the first input, this is the geometry that I want to end up with, so the end result geometry, and we want to create some separate attribute through some other process, and then we want these geometries to talk between each other. So I will input the result of this noise vector in our attribute VOP, and let's step inside. So we can use this import point attribute. Let's look in our second input, so the result of the noise. We will do another import point attribute, and we can point the ptnum to the ptnum for our import point attribute. And since the geometries are exactly the same, so I'm not modifying the point number in any way, and we can turn on the point number display, and all of these point numbers on the geometry on the left will be the same point numbers for the geometry on the right. So let's turn this display off and go inside, and for example, now I'm grabbing the position that's on the second input, so I can, for example, do a mix between our original position and our new position, and if I plug the result, we can now alter the bias and we can update the current position to the other position from the second input. So this is pretty cool. Now in an ideal world, we are not changing the point number with the operations that we do on the separate chain, so on the right over here. But depending on what we are doing, we might run this other set of points through a simulation, or we might do any other operation, and as a result our point number will change. So for example, if I do a blast node after our noise vector, let's set this to point, and we're just gonna grab a few points here. So I'll grab all of these, press enter. So we are deleting some of these points. And like I said, this is just to give you an example. This is not something you would usually do, but it is to illustrate that you might do some operations that will mess up the point number on the second geometry. So if I look at the point numbers for this, if I just look at any one of these points, when we do this blast operation, we can see that these numbers change. If we focus on this one, the numbers change, or we can even just do a sort node here. So if I plug this here, I can use a different settings here. So let's use random, and now we have entirely different point numbers for all of these points, as we can see if I turn this on and off. So now when we go back to our attribute VOP, this will no longer works. As we can see, this is going to give us a completely different result. So this is not really what we want. So what we can do to fix this before we start branching off with our geometries, so over here at our original scatter, and I will actually drop a null, and let's reconnect this node. So we create our scatter, and after this null, we branch off in different operations. So what we can do is we can create an attribute for each point that stores our current point number. So I will drop an attribute VOP here right after our scatter, and I will go inside, and I will grab the point number here and do a bind export and create an attribute based on this point number. So the type will be integer because the point number is an integer type, and let's just name this ID. We can give this any name we want, but usually I go with ID. So let's go up, and now this ID will propagate down our chain, and even if we change the geometry in any way, so no matter what I do on our first chain, and let's maybe just drop a color here, and let's make this another color. So no matter what operations I do over here, and what different operations we do on the separate chain, this ID will be the same after we do all of the operations. So let's maybe, I will use another color here, so maybe blue, and let's scatter fewer points so we can see this more clearly, and I will just decrease the force total count. So I made a visualizer for our ID, so I will turn on this visualizer, and here I created this ID visualizer that simply shows us the value of the ID for each point. So this is similar to how this point number display works. And I can even turn this on as well. So we can see currently here that before we do any changes, so right after we create this ID attribute, we are setting the ID value to be the same as our ptnum. So all of the ID values and the ptnum values stay the same. And now when we do some operations on the right here and we change the point number, if I go to this sort, and let's maybe disable the attribute noise vector so we don't displace them, we see that we have a different point number, but the ID value is the same for the same point. So we can go over here, we can see that the ID matches the PT_num, and then when I look at my sort, we have a different point number but the same ID value. So this will be the same in both of these chains, okay, no matter what I do. So even if I distort the position, or if I delete some points or resort them, our IDs will match. So now we can use this ID value to match the point between the two geometries. And for this we can use the node find attribute value. So let's go inside here, let's drop the find attribute value node. So a super useful node, and let's take a look at this. So we want to look in our second geometry. So let's connect this here to op input 2. And we want to look for the point that has the same ID as our own current IDs. So the ID from the first input, which is our own geometry. So we are looking for an integer attribute. The name is ID. And the search value will be our own ID. So we can do a bind. And we can bring in this ID attribute. So let's set the name here to ID. And this is an integer. And I will connect this ID result as our search value. And let's maybe organize these nodes a little bit, like so. And now this will return the correct point number from the second geometry. So for example, for this point over here, and I'm not sure how well we can see this in the viewport, but for this point, the find attribute value will look at this point and it will look at our ID, which is this 672 value. It will look in the second geometry for the point that has the same ID value, and it will return the point number of that point. So in this case, it's going to be the point number 251. So now we can plug this as our PT_num, and let's go up and let's re-enable our attribute noise, and let's go back inside here. So now when we look at our mix result, let's take a look and let's disable the displays for now, and let's maybe increase the points as well. So I will scatter more points. So now let's look at our mix, and we can see that when we play around with the bias, we are kind of getting the correct result. We have a set of points that are going towards the center of our scene, and we will fix this in a second, but we are kind of there. And let's go up and disable this color node. We no longer need this. Now this set of points that are going towards the center of the scene, and maybe we can see this better with a pixel display. So we can see that some points are going to the center, and these are the points that didn't find their matching ID from the second geometry. So if we look at our points, here we have 22,352 points, and here, because we blasted some points, we end up with less points, so around 20,000. So there will be a 2,000 points difference between the two geometries, and those are the 2,000 points that are converging to the center here. Now the way this find attribute value works is if it couldn't find a point number, it returns a value of -1. So knowing this, we can do a compare, and we can say that if this value is equal to -1, so if it didn't find a point number, we can use the bool result here to do some operations. So I will do a if block, and we don't have to worry about this for now. This is just to illustrate that we do have options with the stray points that aren't finding a matching ID. So I'll plug the condition to be our bool, and let's say that I simply want to remove the points that don't have this matching ID. So I will do a remove point, and then we also have to connect our PT_num to the PT_num here. So let's go ahead and grab the PT_num and do the operation for all of the points. And we can see if I turn this on and off, we are removing all of the points that have a that match our compare condition. And if I go to the mix result now, we are just doing these on only the points that have a matching ID from the second geometry. But we can ignore all of this for now. All I wanted to show is how this find attribute value function works. So this is another super useful node, and it's usually used in combination with import point attribute like the Nearpoint function. And this comes up a lot, especially when we are working with particles, and the particles by default will have an ID Specifically for reasons like this, it stores an ID for each particle because when we spawn more particles, the point numbers change from frame to frame, but the ID remains the same. So we can use the ID, which is consistent for each frame, to do certain operations. So this is the find attribute value. And this here, what I'm doing by combining two different geometries, is just to give you an idea of how the find attribute value works. Let's take a look at some other ways that geometries can interact with each other. So I prepared a scene here. We have a torus, so just a simple torus that's a little bit above the ground. Then we scatter some points on this torus, and then over here we have a grid. And let's not worry about these nodes that are turned off for now, but we plug the points of our torus in the first input in an attribute VOP, and the grid will go in the second input. So let's dive inside the attribute VOP, and we can see nothing is currently happening. And one other way that we can interact between the geometries is by using a minimum position. So let's drop the minimum position node. So this will return to us the closest position that each of these points can find on the second input. So on our grid geometry, it will return the closest position on the primitive. So if I go up real quick, we can see that our grid does have a bunch of primitives. Now it could work with any amount of subdivisions here, and we will see this in a second. So let's go back inside. We want our points to look at our grid, so I will plug the input into the op input 2, which is our grid, and from the position that we currently have, we want to find the closest position on this grid. And if I plug the result in our P, all of our points got flattened, so they found their closest position where they land on this primitive. And if I go back inside, I can maybe do a mix node so we can see this better. So I'll plug this in the second result, and now we can use this bias so we can see exactly the path they travel. So from over here, from their original position, they will find the closest point where they land on this grid. So this is working on the primitives, and if I go up and I reduce the amount of primitives that we have, so if I reduce the rows and columns, we can see that we get the same result. So this is very useful for us because we are always going to have a smooth result, no matter how many points our geometry has. So this is the Minpos, and this is very useful sometimes, but we can see that the result here by default is going to return the position. But let's say we have an attribute on these points and we want to retrieve that attribute, so not necessarily the position. So let's say that maybe we want to grab the normal attribute or the velocity. So for this we can use the XYZDist. So let's drop down an XYZDist node, and this we can see that it has kind of the same inputs as our minimum position. So I will plug the pos into our P, and we will point this to our second input, so our grid. But now we have a few more properties to play around with here. So the distance will simply return the distance between where our points currently are, so over here, and where they land on the geometry, so over here. So it's going to compute this distance between each point. So this is the distance, and this is very useful for some stuff as well. And I will show you an example in a second, but let's move forward, and we have the primitive number. So each of these primitives has a number. If I go to the grid and turn on the primitive number display, it's going to return this number so we can identify the primitive. And let's set this to template and go back to our attribute VOP and disable the point display for the primitives. And then this PrimUV is going to be a vector that tells us exactly where on the primitive we land. So in Houdini, each primitive has this intrinsic UV attribute that goes from 0 to 1 for all of the primitives. So this is different than the regular UVs that we use for texturing and materials. If we look at just one of these primitives, so one of these squares, each of these has a separate intrinsic UV coordinate that we can use to determine where the point lands. So we can imagine that it's something that goes from 0 over here to 1 over here, and then another 0. So it's going to use these coordinates to find the position where our point lands. So again, all primitives have this information, this intrinsic UV. But long story short, this here is just the position where they land on the primitive. So now we can use this information in a primitive node. So if I drop a primitive attribute, let's drop this here. Now we can use this node to retrieve exactly the attribute that we want from our geometry, so from our grid. So I will point the file to op-input2, so again our grid, and then this will ask us for what attribute we want to retrieve. So let's say that we want to retrieve the position. I will set the attribute here to p. And then we have the primitive number, so this one here that we found with the XYZDist. I will plug this here, and then the position on the primitive, so this PrimUV, and I will plug this over here. Now we have this UVW float values, and this is if we want to get extremely specific with the position of the primitives, but I almost never use these values because the UV already has all of these values. This is just in case we want separate values, but that's very rarely the case. Alright, so now we retrieve the position where they fall on this grid. So now if I were to replace this minimum position with our PrimUV, we should get the exact same result. Okay, so I plug this here and we can see that it does the exact same thing that our minimum position did. So I can go to the mix, and this was our original position. So again, with the XYZ distance and the primitive attribute, we retrieved the point where they would fall on our grid. So if I plug this directly inside the P, we can see that this is the result. So again, this is useful if we want to work with other attributes than the position. So in this PrimUV, we can specify what attribute we want to grab from the second geometry. So if I type here n, and we don't have a normal attribute, let's go first up, and I set up some nodes over here. So let's re-enable this node and check that our grid now has normal information on all of the points. When we go back to this attribute VOP, and I plug the result here in our P, but we want to update our own normals, not the position. So let's plug this into the normals. And now we can see that all of the points have normals. So this is the normal that we grab from where they fall on the grid. So I'll get rid of this mix node, and if I were to plug the minimum position into the P, so we can also visualize where they land, we can see what happens. So again, it's going to grab this normal that we have here, it's going to grab it for each point. And it's important to note that it's grabbing the interpolated value of the normal. So if I go to the grid, and I just want to add a few more subdivisions here, and then we add normals to our points. I also have a node here which I use to distort our normal vectors a little bit. So I will enable this node, and we can see that this simply adds a noise for all of the vectors. And for the scatter, let's just focus on a few points here. So I have a blast node, and I will enable this. So we only work with a few set of points. As we can see, it's these points that are a part of the whole geometries. So it's going to be more evident if we only focus on a few select points. So when I go back in our attribute VOP, now they fall on our grid, and it also retrieves the normal. And if I preview the result of our grid at the same time, we can see here, for example, for this point in the middle, it's actually the average between this point and this other point. So it's always going to return to us a smooth interpolated result. So maybe I can increase the rows and columns here. So let's do something like this, and maybe this is now even more apparent. If we look at the normals on the grid over here and over here, we can see that all of the normals on our points have this interpolation between these two vectors. So maybe if I also play around with the offset here, let's make this even more apparent. But hopefully you get this by now. We look at this point on the grid and this other point on the grid, and now all of our own points will have this interpolated result. So this is a key component to having smooth movement in simulations and when doing other operations as well. So like I said, this PrimUV can return any attribute, and it returns the average between the points. So it's extremely useful, and we use this all the time. So the minimum position and XYZDist combined with the primitive attribute are very useful when we are trying to communicate with a geometry that has primitives, and I pretty much use them in maybe 95% of the time, but they have some shortcomings, and I want to demonstrate this. We have the same setup with a torus on which we scatter points, and to the left we have the same grid, so just a flat grid, and let's go inside our attribute VOP, and we are using the minimum position. So in the mix node here, if I change the bias, we can see exactly where they land on our grid. So this is working fine because we are dealing with a flat surface, so we get a pretty consistent result. We kind of retain the shape of our torus. But let's see what happens if we modify our grid. So I will go to this grid and I will enable this edit node where I grabbed a few points and I just moved them up a little bit. So if I go to the result of the minimum position now, we have a very weird result. And if I go inside and change the bias, we can see exactly what's happening here. As I decrease the bias and go back to our original position, we can see, and maybe it's worth if I template our geometry, we can see that from our original position, most of these points will be closer to this part of our geometry. So we no longer get this flat result where they just fall down because the points are simply closer to this part of the geometry. And as I increase the bias, we can see that some of these points are actually closer to this part of the geometry rather than this. But we can see the problem that we have by using the minimum position, and this will be the same for XYZDist as well. So let's say that we want to specify where exactly we want to look in our second geometry, so on this grid geometry. For this we can use an intersect node. So if I drop an intersect node, this is exactly how the ray SOP works if we are familiar with the tool at the SOP level. But this intersect node, I can point this to our grid geometry. So op input 2 will be our file that we want to look in. And now we have a ray origin and a ray direction. So we are going to cast a ray from the position of our points, and we can specify the direction where we want to look in our second geometry. And if I go up, I have a simple setup here with copy to points to demonstrate this. So if I template this result, and let's look at our scatter without doing any modification. So these are the original positions of our points. This is the ray that will intersect with our geometry, so we specify the position exactly where we want to look in our geometries. So I can also template the result of the edit as well. And this is getting a little messy, but hopefully we can see. And if I go to my line here, I can adjust the length so we can see this clearly. So we are casting a ray, and this is the direction which we specify here. So this has a 0, -1, and 0, so a vector that points completely down. And as I increase the length, we have to increase this until we intersect with our geometry. So we have to make sure that this is a big enough vector, so the length of the vector is big enough that it intersects the geometry. So this is all we are doing with the intersect node, and let's go ahead and untemplate all of these. So if I go back inside, the ray origin will be the position of our points, and then the ray direction we are just going to set directly here, and like I mentioned, we are going to give this a vector that points down. So let's do a -1 on the ray direction and 0. Okay, so 0, -1, and 0, vector that points down. And now I can retrieve the position where this would fall on the geometry, or we can even use the same thing as we did with the XYZ distance. We can plug this in a primitive attribute. So if I drop a primitive attribute, so the prim number will go in the prim number and the UVW in the UV, and we have to point the file at our op input 2, so our grid, and then we can specify what attribute we want, so our position. And if I plug this and update our own position, we can see the result. And this is actually not giving us the result we want. We are getting an error here, so this is why all of the points now are at 0. And this is because in our intersect node, even though we specify the direction which we want, so 0, -1, and 0, this direction isn't big enough to intersect our geometry. So we can see actually, if I were to grab this middle value and I were to decrease this value and I start decreasing this, slowly our points are actually going to find the geometry. So let's just decrease this until all of our points and found the geometry, so we no longer have a point here. So we can see that we are reaching a value roughly of -5, and if I go up and I template the scatter, we can preview where our points started. And if I go in a orthographic view, so our right view, we can see that the difference between this and our geometry is roughly 5 units. So we can see there's a 5 here, and we need our rays to reach all the way up to this value here. So the ray has to be big enough in order to reach the geometry. So let's go back inside. So usually with this ray direction vector, once we decide on a vector, so let's say that I want them to point completely straight down, so I set this to -1, I usually just multiply this value, so I add a bunch of zeros here to make sure that the vector is big enough so it intersects any kind of geometry. So now we have the correct result, and we can plug this into the mix to see exactly how they travel. So they go from the original position, they go straight down until they find the position on the geometry. So going back to the regular perspective view, if I template our geometry, we can see where these would land. Now, of course, since we are using the PrimUV here, we can we could retrieve the normal attribute or whatever attribute we want, and it would interpolate the result, just like the XYZ distance. So this intersect is very useful when we want to interact with our geometry, but we want to specify a exact direction from where we want to grab the attributes. Now, like I said, most of the time it's either going to be Minpos or XYZDist, but I did encounter some specific situations where the intersect node proved to be very useful. So minimum position, XYZDist and intersect are all fine when we are dealing with geometry that has primitives, but what happens when we want to interact with a geometry that only has points? So again, we have on the left here a torus, and we scatter some points onto this torus, and we have the same grid, but instead of dealing with primitives, let's only deal with points. So let's scatter some points and work with this. So earlier we used a Nearpoint function to find which of these points are closest to our geometry. So if I template this, probably we can see this better in this attribute VOPS. So I already set up the Nearpoint function that we created earlier. So if I go inside, we are grabbing the nearest point from our second geometry and grabbing the position from the points. And in this mix node now we can see that if I increase the blend, all of the points are going to find their nearest point from the second geometry, and they're all going to move to that position like so. So if I wanted to have a more consistent result and get more of the original torus shape, I would have to go up and I would have to scatter more points, so we would have more information for our position. So if for the second input here, for the second scatter, I scatter more points, so I can increase this. Now we have a bunch of points, as we can see, and if I go back here, when I play around with the bias, we can see that we kind of get the same result that we got with our other operations, so XYZDist, intersect, and all of those when we were dealing with primitives. Now, a lot of times you won't actually have this option to just create more points and fill the gaps in between. So let's go back to just having a few points. So let's go back to our result. Now there is a way that we can still get an interpolated result, so a smooth transition between the points where they are and the points on the second geometry, if we open a point cloud and we retrieve some attributes. So we can use a PCOpen for this. So let's actually keep this attribute VOP with the Nearpoint, and in fact I will rename this to Nearpoint, and let's create our PCOpen in a separate attribute so we can compare. So I will plug this scatter in our first input and our second points in the second input here, and let's rename this to PCOpen, and let's step inside and let's drop a PCOpen node. So if I drop this node, we can see that we have a bunch of inputs over here. Now we can point the file to our second geometry, which is the geometry that we want to look into. So similar to how the other nodes operate as well. And then we want to specify the position from where we want to open this point cloud. So usually this will be our own position, so the position of each point where they are currently. So I will plug the P inside the P here. And then we have some other options here, but we can leave some of these to default. The most important ones are going to be the search radius and the number of points. And the normal channel, query normal, and cone angle, these are usually fine as they are for 99% of cases. So we only have to worry about the radius here and the number of points. So when I increase a radius, we can imagine for each point an invisible sphere that increases. So this is what the search radius is. When I increase this, we increase that imaginary sphere, and then the number of points will tell it how many points we actually want to consider from this radius. So I made a quick setup for this. Let's say we have just a single point here and we want to interact with these points from a scattered geometry. So I'll go to the end result here and preview this invisible sphere that I was talking about, and basically this will be our radius. So we can see that as I increase the radius from this point, we start to grab some points from our second geometry, and I can increase this to add more points to this mix. So this is what the radius will do for us in the PCOpen. So let's go back in this PCOpen, and then the number of points over here, we can specify if we want to look for more points or less points. And the result of this PCOpen will be an integer value. So this PCOpen by itself doesn't really do a lot for us. We have to combine it with other point cloud nodes. So if I hit tab and search for PC, we can see that we really have a lot of operations that we can combine with our PCOpen function. But probably the most useful one for us will be this point cloud filter. So I will drop this, and we can see that inside this PCFilter we can specify a channel. So this is the vector that we want to retrieve from the points that we are doing operation on. And we can point now the handle to our PCOpen result. So we are looking for the position here. And let's actually go up and let's preview the result of the PCOpen. So again, we are operating on scattered points on the torus, and the second input is going to be this geometry. So let's go back here. And now if I were to do a mix between our current position and the result of this PCFilter, let's take a look and let's plug our blend into P. If I go to the result of this PCFilter, so I set the bias to 1, all of our points will end up at origin 0, 0, 0. So this means that our PCOpen couldn't find any point. And this is because the search radius isn't big enough. So if I go up, our points from the torus are pretty far from our points on the grid. So let's go back to our PCOpen, and we have to increase the search radius. So when I increase this, we are starting to get a different result, and let's just set the search radius to a value of 5, so we know that it's big enough to actually find points on the second geometry. And now we can also see something interesting. If I play around with this bias, we can see that the points don't really snap to other points from our second geometry, so I can also template this here. We are no longer going to an individual points. So when I look at the result of the Nearpoint function, that's operating with the same geometries, this is the result when we do the mix. They are snapping to individual points, and when I look at my PCOpen, we can see that we are retaining the shape of our torus much better. So what's happening here is that from all of the points we are opening up this search radius, and we are looking now at more than one point to determine the position. So this PCFilter is going to retrieve sort of the average between points. So now for the PCOpen, the more numbers we consider, so if I increase this number of points, the smoother result we will get. And this will become even more obvious if we tell it to consider just one single point. So if I set this number of points to 1, we are essentially getting the same result as our near points. So we are only looking at the closest point, so we can see that we get exactly the same deal. And as I start to increase the number of points, so we average more points to this result. As I start to increase this, we are considering more and more points, and as a result we will have a smoother interpolation. So if I increase this, we can see that we reach a point, so around 18, from where if we add more points it makes no difference. So there's no point increasing the number of points here. So when we are using this PCOpen and we are opening a point cloud, it's always going to be a balance between the search radius and the number of points, because if we introduce more points over here, this will slow down the operations, and if we increase the search radius here, this will also slow down the operation. So usually we want to use for both of these as low values as we can to get the result that we are after. But both of these values can go really high, so we can really search for maybe 100 or 200 points. This also depends on how many points we are doing the operations on. So if we are opening a point cloud on 5 million points, then these values will be a lot more sensitive. So we only want to use enough radius and enough number of points to get our result. So this is something to be careful with. But hopefully now we get an idea. It's sort of like the near point, but we are considering more points. So we are getting a smoother result. And this is very important in particle simulations because we can see that this operation gives us a very smooth movement. And usually we are going to use this PCOpen when we want a particle simulation to interact with a different geometry. Now, like I mentioned, the PCOpen can work with many other nodes. So like I said, when I type PC in our tab menu, we have all of these, but probably the most important one is going to be this PC filter. So we can grab the P, but we can also interpolate other attributes as well. So again, normal, velocity, and really any other vector. And we can also grab any kind of vector. So maybe we can grab the age of particles and we can get the average of the age. So maybe if we have particles and we want to retrieve the temperature, we can set this to a flow channel and we will just have to type here temperature. So now from the second geometry that has this temperature attribute, we will be able to get that blended value of the temperature, and we will have a smooth result. But like I said, the PC filter is going to be the most important one that we have to know.